Chapter 9 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Chapter 9. Photography in Astronomy. New highways of science have been monumented now and again by the masterful efforts of genius working single-handed. But more often it is a slow-moving time that ripens discovery, and at the proper moment opens some new path to men whose intellectual power is but a willingness to learn. So the annals of astronomical photography do not recount the achievements of extraordinary genius. It would have been strange indeed if the discovery of photography had not been followed by its application to astronomy. The whole range of chemical science contains no experiment of greater inherent interest than the development of a photographic plate. Let but the smallest ray of light fall upon its strangely sensitive surface, and some subtle invisible change takes place. It is then merely necessary to plunge the plate into a properly prepared chemical bath, and the gradual process of developing the picture begins. Slowly, very slowly, the colorless surface darkens wherever light has touched it. Let us imagine that the exposure has been made with an ordinary lens and camera, and that it is a landscape seeming to grow beneath the experimenter's eyes. At first only the most conspicuous objects make their appearance, but gradually the process extends, until finally every tiny detail is reproduced with marvelous fidelity to the original. The photographic plate, when developed in this way, is called a negative, for in nature luminous points or sources of light are bright, while the developing negative turns dark wherever light has acted. And thus the negative, while true to nature, reproduces everything in a reversed way. Bright things are dark, and shadows appear light. For ordinary purposes, therefore, the negative has to be replaced by a new photograph, made by copying it again photographically. In this way it is again reversed, giving us a picture corresponding correctly to the facts as seen. Such a copy from a negative is what is ordinarily called a photograph. Technically, it is known as a positive. One of the remarkable things about the sensitive plate is its complete indifference to the distance from which the light comes. It is ready to yield obediently to the ray of some distant star that may have journeyed, as it were, from the very vanishing point of space, or to the bright glow of an electric light upon the photographer's table. And this quality makes its use especially advantageous in astronomy, since we can gain knowledge of remote stars only by a study of the light they send us. In such study the photographic plate possesses a supreme advantage over the human eye. If the conditions of weather and atmosphere are favorable, an observer looking through an ordinary telescope will see nearly as much at the first glance as he will ever see. Attentive and continued study will enable him to fix details upon his memory, and to record them by means of drawings and diagrams. Occasional moments of especially undisturbed atmospheric conditions will allow him to glimpse faint objects seldom visible. But on the whole, telescopic astronomers add little to their harvest by continued husbandry in the same field of stars. Photography is different. The effect of light upon the sensitive surface of the plate is strictly cumulative. If a given star can bring about a certain result when it has been allowed to act upon the plate for 1 minute, then in 2 or 3 minutes it will accomplish much more. Perhaps a single minute's exposure would have produced a mark scarcely perceptible upon the developed negative. In that case 3 or 4 minutes would give us a perfectly well-defined black image of the star. Thus, by lengthening the exposure, we can make the fainter stars impress themselves upon the plate. If their light is not able to produce the desired effect in minutes, we can let its action accumulate for hours. In this manner it becomes possible and easy to photograph objects so faint that they have never been seen, even with our most powerful telescopes. This achievement ranks high among those which make astronomy appeal so strongly to the imagination. Scientific men are not given to fancies, nor should they be, but the first long exposure photograph must have been an exciting thing. After coming from the observatory, the chemical development was, of course, made in a dark room, so that no additional light might harm the plate until the process was complete. Carrying it out then into the light, that early experimenter cannot but have felt a thrill of triumph, for his hand held a true picture of dim stars to the eye unlighted, lifted into view as if by magic. Plates have been thus exposed as long as 25 hours, and the manner of doing it is very interesting. Of course, it is impossible to carry on the work continuously for so long a period of time, since the beginning of daylight would surely ruin the photograph. In fact, the astronomer must stop before even the faintest streak of dawn begins to redden the eastern sky. Moreover, making astronomical negatives requires excessively close attention, and this it is impossible to give continuously during more than a few hours. But the exposure of a single plate can be extended over several nights without difficulty. It is merely necessary to close the plate holder with a light, tight cover when the first night's work is finished. To begin further exposure of the same plate on another night, we simply aim the photographic telescope at precisely the same point of the sky as before. The light tight plate holder being again opened, the exposure can go on as if there had been no interruption. Astronomers have invented a most ingenious device for making sure that the telescope's aim can be brought back again to the same point with great exactness. And this is a very important matter, for the slightest disturbance of the plate before the second or subsequent portions of the exposure would ruin everything. Instead of a very complete single picture, we should have two partial ones mixed up together in inextricable confusion. To prevent this, photographic telescopes are made double, not altogether unlike an opera glass. One of the tubes is arranged for photography proper, while the other is fitted with lenses suitable for an ordinary visual telescope. The two tubes are made parallel, and thus the astronomer, by looking through the visual glass, can watch objects in the heavens even while they are being photographed. The visual half of the instrument is provided with a pair of very fine cross wires, movable at will in the field of view. These can be made to bisect some little star exactly before beginning the first night's work. Afterward, everything about the instrument having been left unchanged, the astronomer can always assure himself of coming back to precisely the same point of the sky, by so adjusting the instrument that the same little star is again bisected. It must not be supposed, however, that the entire instrument remains unmoved, even during the whole of a single night's exposure, for in that case the apparent motion of the stars as they rise or set in the sky would speedily carry them out of the telescope's field of view. Consequently, this motion has to be counteracted by shifting the telescope so as to follow the stars, and this can be accomplished accurately and automatically by means of clockwork mechanism. Such contrivances have already been applied in the past to visual telescopes, because even then they facilitated the observer's work. They save him the trouble of turning his instrument every few minutes, and allow him to give his undivided attention to the actual business of observation. For photographic purposes the telescope needs to follow the stars far more accurately than in the older kind of observing with the eye. Nor is it possible to make a clock that will drive the instrument satisfactorily and quite automatically. But by means of the second or visual telescope, astronomers can always ascertain whether the clock is working correctly at any given moment. It requires only a glance at the little star bisected by the cross wires, and if there has been the slightest imperfection in the following by the clockwork, the star will no longer be cut exactly by the wires. The astronomer can at once correct any error by putting in operation a very ingenious mechanical device sometimes called a mouse control. He need only touch an electric button and a signal is sent into the clockwork. Instantly there is a shifting of the mechanism, for one of the regular driving wheels is substituted temporarily, another having an extra tooth, and this makes the clock run a little faster so long as the electric current passes. In a similar way, by means of another button, the clock can be made to run slower temporarily, and thus by watching the cross wires continuously and manipulating his two electric buttons, the photographic astronomer can compel his telescope to follow exactly the object under observation, and he can make certain of obtaining a perfect negative. These long exposure plates are intended especially for what may be called descriptive astronomy. With them, as we have seen, advantage is taken of cumulative light effects on the sensitive plate, and the telescope's light gathering and space penetrating powers are vastly increased. We are enabled to carry our researches far beyond the confines of the old visible universe. Extremely faint objects can be recorded, even down to their minutest details, with a fidelity unknown to older visual methods. But at present we intend to consider principally applications of photography in the astronomy of measurement, rather than the descriptive branch of our subject. Instead of describing pictures made simply to see what certain objects look like in the sky, we shall consider negatives intended for precise measurement, with all that the word precision implies in celestial science. Taking up first the photography of stars, we must begin by mentioning the work of Rutherford at New York. More than 30 years ago he had so far perfected methods of stellar photography that he was able to secure excellent pictures of stars as faint as the 9th magnitude. In those days the modern process of dry plate photography had not been invented. Today plates exposed in the photographic telescope are made of glass covered with a perfectly dry film of sensitized gelatin. But in the old wet plate process the sensitive film was first wetted with a chemical solution, and this solution could not be allowed to dry during the exposure. Consequently, Rutherford was limited to exposures of a few minutes in length, while nowadays, as we have said, their duration can be prolonged at will. When we add to this the fact that the old plates were far less sensitive to light than those now available, it is easy to see what were the difficulties in the way of photographing faint stars in Rutherford's time. Nor did he possess the modern ingenious device of a combined visual and photographic instrument. He had no electric controlling apparatus. In fact, the younger generation of astronomers can form no adequate idea of the patience and personal skill Rutherford must have had at his command, for he certainly did produce negatives that are but little inferior to the best that can be made today. His only limitation was that he could not obtain images of stars much below the 9th magnitude. To understand just what is meant here by the 9th magnitude, it is necessary to go back in imagination to the time of Hipparchus, the father of sidereal astronomy. He adopted the convenient plan of dividing all the stars visible to the naked eye, of course he had no telescope, into 6 classes, according to their brilliancy. The faintest visible stars were put in the 6th class, and all the others were assigned somewhat arbitrarily to one or the other of the brighter classes. Modern astronomers have devised a more scientific system, which has been made to conform very nearly to that of Hipparchus, just as it has come down to us through the ages. We have adopted a certain arbitrary degree of luminosity as the standard 1st magnitude, compared with sunlight. This may be represented roughly by a fraction of which the numerator is 1, and the denominator about 80,000 millions. The standard 2nd magnitude star is one whose light, compared with the 1st magnitude, may be represented approximately by the fraction 2/5. The third magnitude in turn may be compared with the second by the same fraction, 2/5. And so the classification is extended to magnitudes below those visible to the unaided eye. Each magnitude compares with the one above it, as the light of 2 candles would compare with the light of 5. Rutherford did not stop with mere photographs. He realized very clearly the obvious truth that by making a picture of the sky we simply change the scene of our operations. Upon the photograph we can measure that which we might have studied directly in the heavens, but so long as they remain unmeasured, celestial pictures have a potential value only. Locked within them may lie hidden some secret of our universe, but it will not come forth unsought. Patient effort must precede discovery in photography, as elsewhere in science. There is no royal road. Rutherford devised an elaborate measuring machine in which his photographs could be examined under the microscope with the most minute exactness. With this machine he measured a large number of his pictures, and it has been shown quite recently that the results obtained from them are comparable in accuracy with those coming from the most highly accredited methods of direct eye observation. And photographs are far superior in ease of manipulation. Convenient day observing under the microscope in a comfortable astronomical laboratory is substituted for all the discomforts of a midnight vigil under the stars. The work of measurement can proceed in all weathers, whereas formerly it was limited strictly to perfectly clear nights. And lastly, the negatives form a permanent record to which we can always return to correct errors or re-examine doubtful points. Rutherford's stellar work extended down to about 1877, and included especially parallax determinations and the photography of star clusters. Each of these subjects is receiving close attention from later investigators, and therefore merits brief mention here. Stellar parallax is in one sense but another name for stellar distance. Its measurement has been one of the most important problems of astronomy for centuries, ever since men recognized that the Copernican theory of our universe requires the determination of stellar distances for its complete demonstration. If the earth is swinging around the sun once a year in a mighty path or orbit, there must be changes of its position in space comparable in size with the orbit itself, and the stars ought to shift their apparent places on the sky to correspond with these changes in the terrestrial observer's position. The phenomenon is analogous to what occurs when we look out of a room, first through one window and then through another. Any object on the opposite side of the street will be seen in a changed direction, on account of the observer's having shifted his position from one window to the other. If the object seem to be due north when seen from the first window, it will perhaps appear a little east of north from the other. But this change of direction will be comparatively small if the object under observation is very far away, in comparison with the distance between the two windows. This is what occurs with the stars. The earth's orbit, vast as it is, shrinks into almost absolute insignificance when compared with the profound distances by which we are sundered from even the nearest fixed stars. Consequently, the shifting of their positions is also very small, so small as to be near the extreme limit separating that which is measurable from that which is beyond human ken. Photography lends itself most readily to a study of this matter. Suppose a certain star is suspected of having a parallax. In other words, we have reason to believe it's near enough to admit of a successful measurement of distance. Perhaps it is a very bright star, and other things being equal, it is probably fair to assume that brightness signifies nearness. And astronomers have certain other indications of proximity that guide them in the selection of proper objects for investigation, though such evidence, of course, never takes the place of actual measurement. The star under examination is sure to have near to it on the sky a number of stars so very small that we may safely take them to be immeasurably far away. The Parallax star is among them, but not of them. We see it projected upon the background of the heavens, though it may in reality be quite near us, astronomically speaking. If this is really so, and the star therefore subject to the slight parallactic shifting already mentioned, we can detect it by noting the suspected star's position among the surrounding small stars, for these, being immeasurably remote, will remain unchanged within the limits of our powers of observation, and thus serves as points of reference for marking the apparent shifting of the brighter star we are actually considering. We have merely to photograph the region at various seasons of the year. Careful examination of the photographs under the microscope will then enable us to measure the slightest displacement of the parallax star. From these measures, by a process of calculation, astronomers can then obtain the star's distance. It will not become known in miles. We shall only ascertain how many times the distance between the earth and sun would have to be laid down like a measuring rod, in order to cover the space separating us from the star, and the subsequent evaluation of this distance, earth to sun, in miles, is another important problem in whose solution photography promises to be most useful. The above method of measuring stellar distance is of course subject to whatever slight uncertainty arises from the assumption that the small stars used for comparison are themselves beyond the possibility of parallactic shifting. But astronomy possesses no better method. Moreover, the number of small stars used in this way is, of course, much larger in photography than it ever can be in visual work. In the former process, all surrounding stars can be photographed at once. In the latter, each star must be measured separately, and daylight soon intervenes to impose a limit on numbers. Usually only two can be used, so that here photography has a most important advantage. It minimizes the chance of our parallax being rendered erroneous by the stars of comparison not being really infinitely remote. This might happen perhaps in the case of one or two, but with an average result from a large number we know to be practically impossible. Cluster work is not altogether unlike parallax hunting in its preliminary stage of securing the photographic observations. The object is to obtain an absolutely faithful picture of a star group, just as it exists in the sky. We have every reason to suppose that a very large number of stars condensed into one small spot upon the heavens mean something more than chance aggregation. The Pleiades group contains thousands of massive stars, doubtless held together by the force of their mutual gravitational attraction. If this be true, there must be complex orbital motion in the cluster, and as time goes on we should actually see the separate components change their relative positions, as it were, before our eyes. The details of such motion upon the great scale of cosmic space offers one of the many problems that make astronomy the grandest of human sciences. We have said that time must pass before we can see these things. There may be centuries of waiting, but one way exists to hurry on the perfection of our knowledge. We must increase the precision of observations. Motions that would need the growth of centuries to become visible to the older astronomical appliances might yield in a few decades to more delicate observational processes. Here photography is most promising. Having once obtained a surpassingly accurate picture of a star cluster, we can subject it easily to precise microscopic measurement. The same operations, repeated at a later date, will enable us to compare the two series of measures, and thus ascertain the motions that may have occurred in the interval. The Rutherford photographs furnish a veritable mine of information in researches of this kind, for they antedate all other celestial photographs of precision by at least a quarter century. and bring just so much nearer the time when definite knowledge shall replace information based on reasoning from probabilities. Rutherford's methods show the advantages of photography as applied to individual star clusters. It required only the attention of some astronomer disposing of large observational facilities and accustomed to operations upon a great scale, to apply similar methods throughout the whole heavens. In the year 1882 a bright comet was very conspicuous in the southern heavens. It was extensively observed from the southern hemisphere, and especially at the British Royal Observatory at the Cape of Good Hope. Gill, director of that institution, conceived the idea that this comet might be bright enough to photograph. At that time comet photography had been attempted but little, if at all, and it was by no means sure that the experiment would be successful. Nor was Gill well acquainted with the work of Rutherford, for the best results of that astronomer had lain dormant many years. He was one of those men with whom personal modesty amounts to a fault. Loath to put himself forward in any way, and disliking to rush into print, Rutherford had given but little publicity to his work. This peculiarity has doubtless delayed his just reputation, but he will lose nothing in the end from a brief postponement. Gill must, however, be credited with more penetration than would be his due if Rutherford had made it possible for others to know that he had anticipated many of the newer ideas. However this may be, the comet was photographed with the help of a local portrait photographer named Alice. When Gill and Alice fastened a simple portrait camera belonging to the latter upon the tube of one of the Cape telescopes, and pointed it at the great comet, they little thought the experiment would lead to one of the greatest astronomical works ever attempted by men. And yet this was destined to occur. The negative they obtained showed an excellent picture of the comet, but what was more important for the future of sidereal astronomy, it was also quite thickly dotted with little black points corresponding to stars. The extraordinary ease with which the whole heavens could be thus charted photographically was brought home to Gill as never before. It was this comet picture that interested him in the application of photography to star charting, and without his interest the now famous astrophotographic catalogue of the heavens would probably never have been made. After considerable preliminary correspondence, a congress of astronomers was finally called to meet at Paris in 1887. Representatives of the principal observatories and civilized governments were present. They decided that the end of the 19th century should see the making of a great catalogue of all the stars in the sky upon a scale of completeness and precision surpassing anything previously attempted. It is impossible to exaggerate the importance of such a work, for upon our star catalogues depends ultimately the entire structure of astronomical science. The work was far too vast for the powers of any observatory alone. Therefore the whole sky from pole to pole was divided into 18 belts or zones of approximately equal area, and each of these was assigned to a single observatory to be photographed. A series of telescopes was specially constructed so that every part of the work should be done with the same type of instrument. As far as possible, an attempt was made to secure uniformity of methods, and particularly a uniform scale of precision. To cover the entire sky upon the plan proposed, no less than 44,108 negatives are required, and most of these have now been finished. The further measurement of the pictures and the drawing up of a vast printed star catalogue are also well under way. One of the participating observatories, that at Potsdam, Germany, has published the first volume of its part of the catalogue. It is estimated that this observatory alone will require 20 quarto volumes to contain merely the final results of its work on the catalogue. Altogether not less than 2,000,000 stars will find a place in this, our latest directory of the heavens. Such wholesale methods of attacking problems of observational astronomy are particularly characteristic of photography. The great catalogue is perhaps the best illustration of this tendency, but of scarcely smaller interest, though less important in reality, is the photographic method of dealing with minor planets. We have already said that in the space between the orbits of Mars and Jupiter, several hundred small bodies are moving around the sun in ordinary planetary orbits. These bodies are called asteroids, or minor planets. The visual method of discovering unknown members of this group was painfully tedious, but photography has changed matters completely, and has added immensely to our knowledge of the asteroids. Wolf of Heidelberg first made use of the new process for minor planet discovery. His method is sufficiently ingenious to deserve brief mention again. A photograph of a suitable region of the sky was made with an exposure lasting 2 or 3 hours, and throughout all this time the instrument was manipulated so as to follow the motion of the heavens in the way we have already explained, so that each star would appear on the negative as a small round black dot. But if a minor planet happened to be in the region covered by the plate, its photographic image would be very different. For the orbital motion of the planet about the sun would make it move a little among the stars, even in the 2 or 3 hours during which the plate was exposed. This motion would be faithfully reproduced in the picture, so that the planet would appear as a short curved line rather than a well-defined dot like a star. Thus the presence of such a line image infallibly denotes an asteroid. Subsequent calculations are necessary to ascertain whether the object is a planet already known or a genuine new discovery. Wolf and others, using his method in recent years, have made immense additions to our catalogue of asteroids. Indeed, the matter was beginning to lose interest on account of the frequency and sameness of these discoveries, when the astronomical world was startled by the finding of the planet of 1898. On August 27, 1898, Witt of Britain discovered the small body that bears the number 433 in the list of minor planets, and has received the name Eros. Its important peculiarity consists in the exceptional position of the orbit. While all the other asteroids are farther from the sun than Mars, and less distant than Jupiter, Eros can pass within the orbit of the former. At times, therefore, it will approach our earth more closely than any other permanent member of the solar system, excepting our own moon, and so it is in a sense our nearest neighbor, and this fact alone makes it the most interesting of all the minor planets. The 19th century was opened by Piazzi's well-known discovery of the first of these bodies. It is therefore fitting that we should find the most important one at its close. We are almost certain that it will be possible to make use of Eros to solve with unprecedented accuracy the most important problem in all astronomy, and this is the determination of our earth distance from the sun. When considering stellar parallax, we have seen how our observations enable us to measure some of the stars' distances in terms of the distance earth to sun as a unit. It is indeed the fundamental unit for all astronomical measures, and its exact evaluation has always been considered the basal problem of astronomy. Astronomers know it as the problem of solar parallax. We shall not here enter into the somewhat intricate details of this subject. However interesting they may be, the problem offers difficulties somewhat analogous to those confronting a surveyor who has to determine the distance of some inaccessible terrestrial point. To do this, it is necessary first to measure a base line, as we call it. Then the measurement of angles with a theodolite will make it possible to deduce the required distance of the inaccessible point by a process of calculation. To ensure accuracy, however, as every surveyor knows, the base line must be made long enough, and this is precisely what is impossible in the case of the solar parallax. For we are necessarily limited to marking out our base line on the earth, and the entire planet is too small to furnish one of really sufficient size. The best we can do is to use the distance between two observatories situated as near as may be on opposite sides of the earth. But even this base is woefully small. However, the smallness loses some of its harmful effect if we operate upon a planet that is comparatively near us. We can measure such a planet's distance more accurately than any other, and this being known, the solar distance can be computed by the aid of mathematical considerations based upon Newton's law of gravitation and observational determinations of the planetary orbital elements. Photography is by no means limited to investigations in the older departments of astronomical observation. Its powerful arm has been stretched out to grasp as well the newer instruments of spectroscopic study. Here the sensitive plate has been substituted for the human eye with even greater relative advantage. The accurate microscopic measurement of difficult lines in stellar spectra was indeed possible by older methods. But photography has made it comparatively easy, and above all has rendered practicable series of observations extensive enough in numbers to furnish statistical information of real value. Only in this way have we been able to determine whether the stars, in their varied and unknown orbits, are approaching us or moving farther away. Even the speed of this approach or recession has become measurable, and has been evaluated in the case of many individual stars. The subject of solar physics has become a veritable department of astronomy in the hands of photographic investigators, and ingenious spectrophotographic methods have been devised, whereby we have secured pictures of the sun from which we have learned much that must have remained forever unknown to older methods. Especially useful has photography proved itself in the observation of total solar eclipses. It is only when the sun's bright disk is completely obscured by the interposed moon that we can see the faintly luminous structure of the solar corona, that great appendage of our sun, whose exact nature is still unexplained. Only during the few minutes of total eclipse in each century can we look upon it, and keen is the interest of astronomers when those few minutes occur. But it is found that the eye observations made in hurried excitement have comparatively little value. Half a dozen persons might make drawings of the corona during the same eclipse, and yet they would differ so much from one another as to leave the true outline very much in doubt. But with photography we can obtain a really correct picture whose details can be studied and discussed subsequently at leisure. If we were asked to sum up in one word what photography has accomplished, we should say that observational astronomy has been revolutionized. There is today scarcely an instrument of precision in which the sensitive plate has not been substituted for the human eye. Scarcely an inquiry possible to the older method which cannot now be undertaken upon a grander scale. Novel investigations, formerly not even possible, are now entirely practicable by photography, and the end is not yet. Valuable as the achievements already consummated, photography is richest in its promise for the future. Astronomy has been called the perfect science. It is safe to predict that the next generation will wonder that the knowledge we have today should ever have received so proud a title. End of chapter 9.
Chapter 10 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Time Standards of the World. The question is often asked, what is the practical use of astronomy? We know, of course, that men would profit greatly from a study of that science, even if it could not be turned to any immediate bread-and-butter use. For astronomy is essentially the science of big things, and it makes men bigger to fix their minds on problems that deal with vast distances and seemingly endless periods of time. No one can look upon the quietly shining stars without being impressed by the thought of how they burned, then as now, before he himself was born, and so shall continue after he has passed away, aye, even after his latest descendants shall have vanished from the earth. Of all the sciences, astronomy is at once the most beautiful poetically, and yet the one offering the grandest and most difficult problems to the intellect. A study of these problems has ever been a labor of love to the greatest minds. Their solution has been counted justly among man's loftiest achievements. And yet of all the difficult and abstruse sciences, astronomy is, perhaps, the one that comes into the ordinary practical daily life of the people more definitely and frequently than any other. There exist at least 3 things we owe to astronomy that must be regarded as quite indispensable, from a purely practical point of view. In the first place, let us consider the maps in a work on geography. How many people ever think to ask how these maps are made? It is true that the ordinary processes of the surveyor would enable us to draw a map showing the outlines of a part of the earth's surface. Even the locations of towns and rivers might be marked in this way. But one of the most important things of all could not be added without the aid of astronomical observations. The latitude and longitude lines, which are essential to show the relation of the map to the rest of the earth, we owe to astronomy. The longitude lines, particularly, as we shall see farther on, play a most important part in the subject of time. The second indispensable application of astronomy to ordinary business affairs relates to the subject of navigation. How do ships find their way across the ocean? There are no permanent marks on the sea, as there are on the land, by which the navigator can guide his course. Nevertheless, seamen know their path over the trackless ocean with a certainty as unerring as would be possible on shore, and it is all done by the help of astronomy. The navigator's observations of the sun are astronomical observations. The tables he uses in calculating his observations, the tables that tell him just where he is and in what direction he must go, are astronomical tables. Indeed, it is not too much to say that without astronomy there could be no safe ocean navigation. But the third application of astronomy is of still greater importance in our daily life: the furnishing of correct time standards for all sorts of purposes. It is to this practical use of astronomical science that we would direct particular attention. Few persons ever think of the complicated machinery that must be put in motion in order to set a clock. A man forgets some evening to wind his watch at the accustomed hour. The next morning he finds it run down. It must be reset. Most people simply go to the nearest clock, or ask some friend for the time, so as to start the watch correctly. More careful persons, perhaps, visit the jeweller's and take the time from his regulator. But the regulator itself needs to be regulated. After all, it is nothing more than any other clock, except that greater care has been taken in the mechanical construction and arrangement of its various parts. Yet it is but a machine built by human hands, and, like all human works, it is necessarily imperfect. No matter how well it has been constructed, it will not run with perfectly rigid accuracy. Every day there will be a variation from the true time by a small amount, and in the course of days or weeks the accumulation of these successive small amounts will lead to a total of quite appreciable size. Just as the ordinary citizen looks to the jeweller's regulator to correct his watch, so the jeweller applies to the astronomer for the correction of his regulator. Ever since the dawn of astronomy, in the earliest ages of which we have any record, the principal duty of the astronomer has been the furnishing of accurate time to the people. We shall not here enter into a detailed account, however interesting it would be, of the gradual development by which the very perfect system at present in use has been reached, but shall content ourselves with a description of the methods now employed in nearly all the civilized countries of the world. In the first place, every observatory is, of course, provided with what is known as an astronomical clock. This instrument, from the astronomer's point of view, is something very different from the ordinary popular idea. To the average person, an astronomical clock is a complicated and elaborate affair, giving the date, day of the week, phases of the moon, and other miscellaneous information. But in reality, the astronomer wants none of these things. His one and only requirement is that the clock shall keep as near uniform time as may be possible to a machine constructed by human hands. No expense is spared in making the standard clock for an observatory. Real artists in mechanical construction, men who have attained a world-wide celebrity for delicate skill in fashioning the parts of a clock, such are the astronomers' clockmakers. To increase precision of motion in the train of wheels, it is necessary that the mechanism be as simple as possible. For this reason all complications of date, etc., are left out. We have even abandoned the usual convenient plan of having the hour and minute hands mounted at the same centre, for this kind of mounting makes necessary a slightly more intricate form of wheelwork. The astronomer's clock usually has the centres of the second hand, minute hand, and hour hand in a straight line, and equally distant from each other. Each hand has its own dial, all drawn, of course, upon the same clock face. Even after such a clock has been made as accurately as possible, it will, nevertheless, not give the very best performance unless it is taken care of properly. It is necessary to mount it very firmly indeed. It should not be fastened to an ordinary wall, but a strong pier of masonry or brick must be built for it on a very solid foundation. Moreover, this pier is best placed underground in a cellar, so that the temperature of the clock can be kept nearly uniform all the year round. For we find that clocks do not run quite the same in hot weather as they do in cold. Makers have, indeed, tried to guard against this effect of temperature by ingenious mechanical contrivances. But these are never quite perfect in their action, and it is best not to test them too severely by exposing the clock to sharp changes of heat and cold. Another thing affecting the going of fine clocks, strange as it may seem, is the variation of barometric pressure. There is a slight but noticeable difference in their running when the barometer is high and when it is low. To prevent this, some of our best clocks have been enclosed in air-tight cases, so that outside barometric changes may not be felt in the least by the clock itself. But even after all this has been accomplished, and the astronomer is in possession of a clock that may be called a masterpiece of mechanical construction, he is not any better off than was the jeweller with his regulator. After all, even the astronomical clock needs to be set, and its error must be determined from time to time. A final appeal must then be had to astronomical observations. The clock must be set by the stars and sun. For this purpose the astronomer uses an instrument called a transit. This is simply a telescope of moderate size, possibly 5 or 6 feet long, and firmly attached to an axis at right angles to the tube of the telescope. This axis is supported horizontally in such a way that it points as nearly as may be exactly east and west. The telescope itself, being square with the axis, always points in a north and south direction. It is possible to rotate the telescope about its axis so as to reach all parts of the sky that are directly north or south of the observatory. In the field of view of the telescope certain very fine threads are mounted so as to form a little cross. As the telescope is rotated, this cross traces out, as it were, a great circle on the sky, and this great circle is called the astronomical meridian. Now we are in possession of certain star tables, computed from the combined observations of astronomers in the last 150 years. These tables tell us the exact moment of time when any star is on the meridian. To discover, therefore, whether our clock is right on any given night, it is merely necessary to watch a star with the telescope, and note the exact instant by the clock when it reaches the little cross in the field of view. Knowing from the astronomical tables the time when the star ought to have been on the meridian, and having observed the clock time when it is actually there, the difference is, of course, the error of the clock. The result can be checked by observations of other stars, and the slight personal errors of observation can be rendered harmless by taking the mean from several stars. By an hour's work on a fine night, it is possible to fix the clock error quite easily within the 1/20th part of a second. We have not space to enter into the interesting details of the methods by which the astronomical transit is accurately set in the right position, and how any slight residual error in its setting can be eliminated from our results by certain processes of computation. It must suffice to say that practically all time determinations in the observatory depend substantially upon the procedure outlined above. The observatory clock having been once set right by observations of the sky, its error can be redetermined every few days quite easily. Thus, even the small irregularities of its nearly perfect mechanism can be prevented from accumulating until they might reach a harmful magnitude. But we obtain in this way only a correct standard of time within the observatory itself. How can this be made available for the general public? The problem is quite simple with the aid of the electric telegraph. We shall give a brief account of the methods now in use in New York City, and these may be taken as essentially representative of those employed elsewhere. Every day, at noon precisely, an electric signal is sent out by the United States Naval Observatory in Washington. The signal is regulated by the standard clock of the observatory, of course taking account of star observations made on the next preceding fine night. This signal is received in the central New York office of the Telegraph Company, where it is used to keep correct a very fine clock, which may be called the time standard of the Telegraph Company. This clock, in turn, has automatic electric connections, by means of which it is made to send out signals over what are called time wires, that go all over the city. Jewelers, and others who desire correct time, can arrange to have a small electric sounder in their offices connected with the time wires. Thus the ticks of the Telegraph Company's standard clock are repeated automatically in the jeweller's shop, and used for controlling the exactness of his regulator. This, in brief, is the method by which the astronomer's careful determination of correct time is transferred and distributed to the people at large. Having thus outlined the manner of obtaining and distributing correct time, we shall now consider the question of time differences between different places on the earth. This is a matter which many persons find most perplexing, and yet it is essentially quite simple in principle. Travellers, of course, are well acquainted with the fact that their watches often need to be reset when they arrive at their destination, yet few ever stop to ask the cause. Let us consider for a moment our method of measuring time. We go by the sun. If we leave out of account some small irregularities of the sun's motion that are of no consequence for our present purpose, we may lay down this fundamental principle. When the sun reaches its highest position in the sky, it is 12 o'clock, or noon. The sun, as everyone knows, rises each morning in the east, slowly goes up higher and higher in the sky, and at last begins to descend again toward the west. But it is clear that as the sun travels from east to west, it must pass over the eastern one of any two cities sooner than the western one. When it reaches its greatest height over a western city, it has, therefore, already passed its greatest height over an eastern one. In other words, when it is noon, or 12 o'clock, in the western city, it is already after noon in the eastern city. This is the simple and evident cause of time differences in different parts of the country. Of any two places, the eastern one always has later time than the western. When we consider the matter in this way, there is not the slightest difficulty in understanding how time differences arise. They will, of course, be greatest for places that are very far apart in an east and west direction. And this brings us again to the subject of longitude, which, as we have already said, plays an important part in all questions relating to time. For longitude is used to measure the distance in an east and west direction between different parts of the earth. If we consider the earth as a large ball, we can imagine a series of great circles drawn on its surface, and passing directly from the North Pole to the South Pole. Such a circle could be drawn through any point on the earth. If we imagine a pair of them drawn through two cities, such as New York and London, the longitude difference of these two cities is defined as the angle at the North Pole between the two great circles in question. The size of this angle can be expressed in degrees. If we then wish to know the difference in time between New York and London in hours, we need only divide their longitude difference in degrees by the number 15. In this simple way we can get the time difference of any two places. We merely measure the longitude difference on a map, and then divide by 15 to get the time difference. These time differences can sometimes become quite large. Indeed, for two places differing 180 degrees in longitude, the time difference will evidently be no less than 12 hours. Most civilized nations have agreed informally to adopt some one city as the fundamental point from which all longitudes are to be counted. Up to the present we have considered only longitude differences, but when we speak of the longitude of a city, we mean its longitude difference from the place chosen by common consent as the origin for measuring longitudes. The town almost universally used for this purpose is Greenwich, near London, England. Here is situated the British Royal Observatory, one of the oldest and most important institutions of its kind in the world. The great longitude circle passing through the centre of the astronomical transit at the Greenwich Observatory is the fundamental longitude circle of the earth. The longitude of any other town is then simply the angle at the pole between the longitude circle through that town and the fundamental Greenwich one here described. Longitudes are counted both eastward and westward from Greenwich. Thus, New York is in 74 degrees west longitude, while Berlin is in 14 degrees east longitude. This has led to a rather curious state of affairs in those parts of the earth, the longitudes of which are nearly 180 degrees east or west. There are a number of islands in that part of the world, and if we imagine for a moment one whose longitude is just 180 degrees, we shall have the following remarkable result as to its time difference from Greenwich. We have seen that of any two places, the eastern always has the later time. Now, since our imaginary island is exactly 180 degrees from Greenwich, we can consider it as being either 180 degrees east or 180 degrees west. But if we call it 180 degrees east, its time will be 12 hours later than Greenwich. And if we call it 180 degrees west, its time will be 12 hours earlier than Greenwich. Evidently there will be a difference of just 24 hours, or one whole day, between these two possible ways of reckoning its time. This circumstance has actually led to considerable confusion in some of the islands of the Pacific Ocean. The navigators who discovered the various islands naturally gave them the date which they brought from Europe. And as some of these navigators sailed eastward around the Cape of Good Hope, and others westward around Cape Horn, the dates they gave to the several islands differed by just one day. The state of affairs at the present time has been adjusted by a sort of informal agreement. An arbitrary line has been drawn on the map near the 180th longitude circle, and it has been decided that the islands on the east side of this line shall count their longitudes west from Greenwich, and those west of the line shall count longitude east from Greenwich. Thus Samoa is nearly 180 degrees west of Greenwich, while the Fiji Islands are nearly 180 degrees east. Yet the islands are very near each other, though the arbitrary line passes between them. As a result, when it is Sunday in Samoa, it is Monday in the Fiji Islands. The arbitrary line described here is sometimes called the International Date Line. It does not pass very near the Philippine Islands, which are situated in about 120 degrees east longitude, and therefore use a time about 8 hours later than Greenwich. New York, being about 74 degrees west of Greenwich, is about 5 hours earlier in time. Consequently, as we may remark in passing, Philippine time is about 13 hours later than New York time. Thus 5 o'clock Sunday morning, May 1st, in Manila, would correspond to 4 o'clock Saturday afternoon, April 30th, in New York. There is another kind of time which we shall explain briefly, the so-called standard or railroad time, which came into general use in the United States some few years ago, and has since been generally adopted throughout the world. It requires but a few moments' consideration to see that the accidental situation of the different large cities in any country will cause their local times to differ by odd numbers of hours, minutes, and seconds. Thus a great deal of inconvenience has been caused in the past. For instance, a train might leave New York at a certain hour by New York time. It would then arrive in Buffalo some hours later by New York time. But it would leave Buffalo by Buffalo time, which is quite different. Thus there would be a sort of jump in the timetable at Buffalo, and it would be a jump of an odd number of minutes. It would be different in different cities, and very hard to remember. Indeed, as each railway usually ran its trains by the time used in the principal city along its line, it might happen that 3 or 4 different railroad times would be used in a single city where several roads met. This has all been avoided by introducing the standard time system. According to this, the whole country is divided into a series of time zones, 15 degrees wide, and so arranged that the middle line of each zone falls at a point whose longitude from Greenwich is 60, 75, 90, 105, or 120 degrees. The times at these middle lines are therefore earlier than Greenwich time by an even number of hours. Thus, for instance, the 75-degree line is just 5 even hours earlier than Greenwich time. All cities simply use the time of the nearest one of these special lines. This does not result in doing away with time differences altogether. That would, of course, be impossible in the nature of things. But for the complicated odd differences in hours and minutes, we have substituted the infinitely simpler series of differences in even hours. The traveller from Chicago to New York can reset his watch by putting it just 1 hour later on his arrival. The minute hand is kept unchanged, and no New York timepiece need be consulted to set the watch right on arriving. There can be no doubt that this standard time system must be considered one of the most important contributions of astronomical science to the convenience of man. Its value has received the widest recognition, and its use has now extended to almost all civilized countries. France is the only nation of importance still remaining outside the time zone system. In the following table we give the standard time of the various parts of the earth, as compared with Greenwich, together with the date of adopting the new time system. It will be noticed that in certain cases even half-hours have been employed to separate the time zones, instead of even hours, as used in the United States. Table of the world's time standards. When it is noon at Greenwich, it is noon in Great Britain. It is noon in Belgium. The date of adopting standard time system, May 1892. It is noon in Holland, May 1892. It is noon in Spain, January 1901. When it is noon at Greenwich, it is 1 p.m. in Germany, April 1893. It is 1 p.m. in Italy, November 1893. It is 1 p.m. in Denmark, January 1894. It is 1 p.m. in Switzerland, June 1894. It is 1 p.m. in Norway, January 1895. It is 1 p.m. in Austria, railways. When it is noon at Greenwich, it is 1:30 p.m. in Cape Colony, 1892. It is 1:30 p.m. in Orange River Colony, 1892. It is 1:30 p.m. in Transvaal, 1892. It is 2 p.m. in Natal, September 1895. It is 2 p.m. in Turkey, railways. It is 2 p.m. in Egypt, October 1900. It is 8 p.m. in West Australia, February 1895. It is 9 p.m. in Japan, 1896. It is 9:30 p.m. in South Australia, May 1899. It is 10 p.m. in Victoria, February 1895. It is 10 p.m. in New South Wales, February 1895. It is 10 p.m. in Queensland, February 1895. It is 11 p.m. in New Zealand. In the United States and Canada it is 4 a.m. by Pacific time when it is noon at Greenwich. It is 5 a.m. by Mountain time when it is noon at Greenwich. It is 6 a.m. by Central time when it is noon at Greenwich. It is 7 a.m. by Eastern time when it is noon at Greenwich. It is 8 a.m. by Colonial time when it is noon at Greenwich. End of Chapter 10.
Chapter 11 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Deb K. Practical Talks by an Astronomer by Harold Jacoby. Motions of the Earth's Pole. Students of geology have been puzzled for many years by traces remaining from the period when a large part of the Earth was covered with a heavy cap of ice. These shreds of evidence all seem to point to the conclusion that the center of the ice-covered region was quite far away from the present position of the North Pole of the Earth. If we are to regard the pole as very near the point of greatest cold, it becomes a matter of much interest to examine whether the pole has always occupied its present position, or whether it has been subject to slow changes of place upon the Earth's surface. Therefore, the geologists have appealed to astronomers to discover whether they are in possession of any observational evidence tending to show that the pole is in motion. Now we may say at once that astronomical research has not as yet revealed the evidence thus expected. Astronomy has been unable to come to the rescue of geological theory. From about the year 1750, which saw the beginning of precise observation in the modern sense, down to very recent times, astronomers were compelled to deny the possibility of any appreciable motion of the pole. Observational processes, it is true, furnished slightly divergent pole positions from time to time. Yet these discrepancies were always so minute as to be indistinguishable from those slight personal errors that are ever inseparable from results obtained by the fallible human eye. But in the last few years improved methods of observation, coupled with extreme diligence in their application by astronomers generally, have brought to light a certain small motion of the pole which had never before been demonstrated in a reliable way. This motion, it is true, is not of the character demanded by geological theory, for the geologists had been led to expect a motion which would be continuous in the same direction, no matter how slow might be its annual amount. For the vast extent of geologic time would give even the slowest of motions an opportunity to produce large effects, provided its results could be continuously cumulative. Given time enough, and the pole might move anywhere on the earth, no matter how slow might be its tortoise speed. But the small motion we have discovered is neither cumulative nor continuous in one direction. It is what we call a periodic motion, the pole swinging now to one side, and now to the other, of its mean of average position. Thus this new discovery cannot be said to unravel the mysterious puzzle of the geologists. Yet it is not without the keenest interest, even from their point of view, for the proof of any form of motion in a pole previously supposed to be absolutely at rest may mean everything. No man can say what results will be revealed by the further observations now being continued with great diligence. In the first place, it is important to explain that any such motions as we have under consideration will show themselves to ordinary observational processes principally in the form of changes of terrestrial latitudes. Let us imagine a pair of straight lines passing through the center of the earth and terminating, one at the observer's station at the earth's surface, and the other at the point of the equator which is nearest the observer. Then, according to the ordinary definition of latitude, the angle between these two imaginary lines is called the latitude of the point of observation. Now, we know, of course, that the equator is everywhere just 90 degrees from the pole. Consequently, if the pole is subject to any motion at all, the equator must also partake of the motion. Thus, the angle between our two imaginary lines will be affected directly by polar movement, and the latitude obtained by astronomical observation will be subject to quite similar changes. To clear up the whole question, so far as this can be done by the gathering of observational evidence, it is only necessary to keep up a continual series of latitude determinations at several observatories. These determinations should show small variations similar in magnitude to the wobblings of the pole. Let us now consider for a moment what is meant by the axis of the earth. It has long been known that the planet has in general the shape of a ball or sphere. That this is so can be seen at once from the way ships at sea disappear at the horizon, as they go farther and farther from us. We first lose sight of the hull, then slowly and gradually the spars and sails seem to sink down into the ocean. This proves that the earth's surface is curved. That it is more or less like a sphere is evident from the fact that it always casts a round shadow in eclipses. Sometimes the earth passes between the sun and eclipsed moon. Then we see the earth's black shadow projected on the moon, which would otherwise be quite bright. This shadow has been observed in a very large number of such eclipses, and it has always been found to have a circular edge. Well, therefore, the earth is nearly a round ball. It must not be supposed that it is exactly spherical in form. We may disregard the small irregularities of its surface, for even the greatest mountains are insignificant in height when compared with the entire diameter of the earth itself. But even leaving these out of account, the earth is not perfectly spherical. We can describe it best as a flattened sphere. It is as though one were to press a round rubber ball between two smooth boards. It would be flattened at the top and bottom and bulged out in the middle. This is the shape of the earth. It is flattened at the poles and bulges out near the equator. The shortest straight line that can be drawn through the earth's center and terminated by the flattened parts of its surface may be called the earth's axis of figure, and the 2 points where the axis meets the surface are called the poles of figure. But the earth has another axis, called the axis of rotation. This is the one about which the planet turns once in a day, giving rise to the well-known phenomena called the rising and setting of sun, moon, and stars. For these motions of heavenly bodies are really only apparent ones, caused by an actual motion of the observer on the earth. The observer turns with the earth on its axis, and is thus carried past the sun and stars. This daily turning of the earth, then, takes place about the axis of rotation. Now it so happens that all kinds of astronomical observations for the determination of latitude lead to values based on the rotation axis of the earth, and not on its axis of figure. We have seen how the earth's equator, from which we count our latitudes, is everywhere 90 degrees distant from the pole. But this pole is the pole of rotation, or the point at which the rotation axis pierces the earth's surface. It is not the pole of figure. It is clear that the latitude of any observatory will remain constant only if the pole of figure and the rotation pole maintain absolutely the same positions relatively to one another. These two poles are actually very near together indeed. It was supposed for a very long time that they were absolutely coincident, so that there could not be any variations of latitude, but it now appears that they are separated slightly. Strange to say, one of them is revolving around the other in a little curve. The pole of figure is traveling around the pole of rotation. The distance between them varies little, never becoming greater than about 50 feet, and it takes about 14 months to complete a revolution. There are some slight irregularities in the motion, but, in the main, it takes place in the manner here stated. In consequence of this rotation of the one pole about the other, the pole of figure is now on one side of the rotation pole and now on the opposite side, but it never travels continuously in one direction. Thus, as we have already seen, the sort of continuous motion required to explain the observed geological phenomena has not yet been found by astronomers. Observations for the study of latitude variations have been made very extensively within recent years both in Europe and the United States. It has been found practically most advantageous to carry out simultaneous series of observations at two observatories situated in widely different parts of the earth, but having very nearly the same latitude. It is then possible to employ the same stars for observation in both places, whereas it would be necessary to use different sets of stars if there were much difference in the latitudes. There is a special advantage in using the same stars in both places. We can then determine the small difference in latitude between the two participating observatories in a manner which will make it quite free from any uncertainty in our knowledge of the positions on the sky of the stars observed. For, strange as it may seem, our star catalogues do not contain absolutely accurate numbers. Like all other data depending on fallible human observation, they are affected with small errors. But if we can determine simply the difference in latitude of the two observatories, we can discover from its variation the path in which the pole is moving. If, for instance, the observatories are separated by 1/4 the circumference of this globe, the pole will be moving directly toward one of them, when it is not changing its distance from the other one at all. The method was used for 7 years with good effect at the observatories of Columbia University in New York, and the Royal Observatory at Naples, Italy. For obtaining its most complete advantages, it is of course better to establish several observing stations on about the same parallel of latitude. This was done in 1899 by the International Geodetic Association. 2 stations are in the United States, 1 in Japan, and 1 in Sicily. We can, therefore, hope confidently that our knowledge as to the puzzling problem of polar motion will soon receive very material advancement. End of The Motions of the Earth's Pole. Recording by Deb K.
Chapter 12 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Chapter 12. Saturn's Rings. The death of James E. Keeler, director of the Lick Observatory in California, recalls to mind one of the most interesting and significant of later advances in astronomical science. Only 7 years have elapsed since Keeler made the remarkable spectroscopic observations which gave for the first time an ocular demonstration of the true character of those mysterious luminous rings surrounding the brilliant planet Saturn. His results have not yet been made sufficiently accessible to the public at large, nor have they been generally valued at their true worth. We consider this work of Keeler's interesting because the problem of the rings has been a classic one for many generations, and we have been particular also to call it significant because it is pregnant with the possibilities of newer methods of spectroscopic research applied in the older departments of observational astronomy. The troubles of astronomers with the rings began with the invention of the telescope itself. They date back to 1610, when Galileo first turned his new instrument to the heavens. It may be imagined easily that the bright planet Saturn was among the very first objects scrutinized by him. His powerful instrument, magnified only about 30 times, and was doubtless much inferior to our pocket telescopes of today. But it showed, at all events, that something was wrong with Saturn. Galileo put it, ultimam planetam tergeminam observavi. I have observed the furthest planet to be triple. It is easy to understand now how Galileo's eyes deceived him. For a round, luminous ball like Saturn, surrounded by a thin, flat ring, seen nearly edgewise, really looks as if it had two little attached appendages. Strange indeed it is today to read a scientific book so old that the planet Saturn could be called the furthest planet. But it was the outermost one known in Galileo's day, and for nearly 2 centuries afterward, not until 1781, did William Herschel discover Uranus, and Neptune was not disclosed by the marvelous mathematical perception of Leverrier until 1846. Galileo's further observations of Saturn bothered him more and more. The planet's behavior became much worse as time went on. Has Saturn devoured his children, according to the old legend? He inquired soon afterward, for the changed positions of Earth and planet in the course of their motions around the sun in their respective orbits had become such that the ring was seen quite edgewise, and was therefore perfectly invisible to Galileo's optic tube. The puzzle remained unsolved by Galileo. It was left for another great man to find the true answer. Huygens, in 1656, first announced that the ring is a ring. The manner in which this announcement was made is characteristic of the time. Today it seems almost ludicrous. Huygens published a little pamphlet in 1656 called De Saturni Luna Observatorio Nova, or A New Observation of Saturn's Moon. He gave the explanation of what had been observed by himself and preceding astronomers in the form of a puzzle or logogryph. Here is what he had to say of the phenomenon in question. A, C, D, E, G, H, I, L, M, N, O, P, Q, R, S, T, U. It was not until 1659, 3 years later, in a book entitled Systema Saturnium, that Huygens rearranged the above letters in their proper order, giving the Latin sentence Annulo cingetur tenu pleno nusquam coherente ad eclipticam inclinato. Translated into English, this sentence informs us that the planet is girdled with a thin flat ring, nowhere touching Saturn, and inclined to the ecliptic. This was a perfectly correct and wonderful, sagacious explanation of those complex and exasperatingly puzzling phenomena that had been too difficult for no less a person than Galileo himself. It was an explanation that explained. The reason for its preliminary announcement in the above manner must have been the following. Huygens was probably not quite sure of his ground in 1656, while 3 years afterwards he had become quite certain. By the publication of the logogryph of 1656, he secured for himself the credit of what he had done. If any other astronomer had published the true explanation after 1656, Huygens could have proved his claim to priority by rearranging the letters of his puzzle. On the other hand, if further researches showed him that he was wrong, he would never have made known the true meaning of his logogryph, and would thus have escaped the ignominy of making an erroneous explanation. Thus the method of announcement was comparable in ingenuity with the Huygenian explanation itself. We are compelled to pass over briefly the entertaining history of subsequent observations of the ring, in order to explain the new work of Keeler and others. Cassini, about 1675, has been able to show that the ring was double, that there were really 2 independent rings with a distinct dark space between them. It was a case of wheels within wheels. To our eminent countryman, W.C. Bond of Cambridge, Massachusetts, we owe the further discovery, Harvard College Observatory, November of 1850, of the third ring. This is also concentric with the other two, and interior to them, but difficult to observe because of its much smaller luminosity. It is almost transparent, and the brilliant light of the planet's central ball is capable of shining directly through it. For this reason the inner ring is called the gauze or crape ring. If we add to the above details the fact that our modern large telescopes show slight irregularities in the surface of the rings, especially when seen edgewise, we have a brief statement of all that the telescope has been able to reveal to us since Galileo's time. But of far greater interest than the mere fact of their existence is the important cosmic question as to the constitution, structure, and above all durability of the ring system. Astronomers often use the term stability with regard to celestial systems like the ring system of Saturn. By this they mean permanent durability. A system is stable if its various parts can continue in their present relationship to one another without violating any of the known laws of astronomy. Whenever we study any collection of celestial objects and endeavor to explain their motions and peculiarities, we always seek some explanation not inconsistent with the continued existence of the phenomena in question. For this there is perhaps no sufficient philosophical basis. Probably much of the great celestial procession is but a passing show, to be but for a moment in the endless vista of cosmic time. However this may be, we are bound to assume as a working theory that Saturn has always had these rings and will always have them, and it is for us to find out how this is possible. The problem has been attacked mathematically by various astronomers, including Laplace, but no conclusive mathematical treatment was obtained until 1857, when James Clerk Maxwell proved in a masterly manner that the rings could be neither solid nor liquid. He showed indeed that they would not last if they were continuous bodies like the planets. A big solid wheel would inevitably be torn asunder by any slight disturbance, and then precipitated upon the planet's surface. Therefore the rings must be composed of an immense number of small detached particles, revolving around Saturn in separate orbits like so many tiny satellites. This mathematical theory of the ring system being once established, astronomers were more eager than ever to obtain a visual confirmation of it. We had indeed a sort of analogy in the assemblage of so-called minor planets, which are known to be revolving around our sun in orbits situated between Mars and Jupiter. Some hundreds of these are known to exist, and probably there are countless others too small for us to see. Such a swarm of tiny particles of luminous matter would certainly give the impression of a continuous solid body if seen from a distance comparable to that separating us from Saturn. But arguments founded on analogy are of comparatively little value. Astronomers need direct and conclusive telescopic evidence, and this was lacking until Keeler made his remarkable spectroscopic observation in 1895. The spectroscope is a peculiar instrument, different in principle from any other used in astronomy. We study distant objects with it by analyzing the light they send us, rather than by examining and measuring the details of their visible surfaces. The reader will recall that according to the modern undulatory theory, light consists simply of a series of waves. Now the nature of waves is very far from being understood in the popular mind. Most people, for instance, think that the waves of ocean consist of great masses of water rolling along the surface. This notion doubtless arises from the behavior of waves when they break upon the shore, forming what we call surf. When a wave meets with an immovable body like a sand beach, the wave is broken and the water really does roll upon the beach, But this is an exceptional case. Farther away from the shore, where the waves are unimpeded, they consist simply of particles of water moving straight up and down. None of the water is carried by mere wave action away from the point over which it was situated at first. Tides or other causes may move the water, but not simple wave motion alone. That this is so can be proved easily. If a chip of wood be thrown overboard from a ship at sea, it will be seen to rise and fall a long time on the waves, but it will not move. Similarly, wind waves are often quite conspicuous on a field of grain, but they are caused by individual grain particles moving up and down. The grain certainly cannot travel over the ground, since each particle is fast to its own stalk. But while the particles do not travel, the wave disturbance does. At times it is transmitted to a considerable distance from the point where it was first set in motion. And thus, when a stone is dropped into still water, the disturbance, though not the water, travels in ever widening circles, until at last it becomes too feeble for us to perceive. Light is just such a traveling wave disturbance. Beginning perhaps in some distant star, it travels through space, and finally the wave impinges on our eyes, like the ocean wave breaking on a sand beach. Such a light wave affects the eye in some mysterious way. We call it seeing. The spectroscope enables us to measure and count the waves reaching us each second from any source of light. No matter how far away the origin of stellar light may be, the spectroscope examines the character of that light and tells us the number of waves set up every second. It is this characteristic of the instrument that has enabled us to make some of the most remarkable observations of modern times. If the distant star is approaching us in space, more light waves per second will reach us than we should receive from the same star at rest. And thus, if we find from the spectroscope that there are too many waves, we know that the star is coming nearer, and if there are too few, we can conclude with equal certainty that the star is receding. Keeler was able to apply the spectroscope in this way to the planet Saturn and to the ring system. The observations required dexterity and observational manipulative skill in a superlative degree. These Keeler had, and this work of his will always rank as a classic observation. He found by examining the light waves from opposite sides of the planet that the luminous ball rotated, for one side was approaching us and the other receding. This observation was, of course, in accord with the known fact of Saturn's rotation on his axis. With regard to the rings, Keeler showed in the same way the existence of an actual rotation, which appears not to have been satisfactorily proved before, strange as it may seem. But the crucial point established by his spectroscope was that the interior parts of the rings rotated faster than the exterior. The velocity of rotation diminishes gradually from the inside to the outside, and this fact is absolutely inconsistent with the motion of a solid ring, but it fits in admirably with the theory of a ring comprised of a vast assemblage of small, separate particles. Thus, for the first time, astronomy comes into possession of an observational determination of the nature of Saturn's rings, and Galileo's puzzle is forever solved. End of chapter 12. Chapter 13 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Practical Talks by an Astronomer by Harold Jacoby. Chapter 13. The Heliometer. Astronomical discoveries are always received by the public with keen interest. Every new fact read in the great open book of nature is written eagerly into the books of men. For there exists a strong curiosity to ascertain just how the greater world is built and governed. And it must be admitted that astronomers have been able to satisfy that curiosity with no small measure of success. But it is seldom that we hear of the means by which the latest and most refined astronomical observations are effected. Popular imagination pictures the astronomer as he doubtless once was, an aged gentleman, usually having a long white beard, and spending entire nights staring at the sky through a telescope. But the facts today are very different. The working astronomer is an active man in the prime of life, often a young man. He wastes no time in stargazing. His observations consist of exact measurements made in a precise, systematic, and almost businesslike manner. A night's watch at the telescope is seldom allowed to exceed about 3 hours, since it is found that more continued exertions fatigue the eye and lead to less accurate results. To this, of course, there have been many notable exceptions, for endurance of sight, like any form of physical strength, differs greatly in different individuals. Astronomical research does not include picking out the constellations and learning the Arabic names of individual stars. These things are not without interest, but they belong to astronomy's ancient history and are of little value except to afford amusement and instruction to successive generations of amateurs. Among the instruments for carefully planned measurements of precision, the heliometer probably takes first rank. It is at once the most exquisitely accurate in its results, and the most fatiguing to the observer, of all the varied apparatus employed by the astronomer. The principle upon which its construction depends is very peculiar. It applies to all telescopes, even ordinary ones for terrestrial purposes. If part of a telescope lens be covered up with the hand, it will still be possible to see through the instrument. The glass lens at the end of the tube farthest from the observer's eye helps to magnify distant objects and make them seem nearer by gathering to a single point or focus a greater amount of their light than could be brought together by the far smaller lens in the unaided eye. The telescope might very properly be likened to an enlarged eye, which can see more than we can simply because it is bigger. If a telescope lens has a surface 100 times as large as that of the lens in our eye, it will gather and bring to a focus 100 times as much light from a distant object. Now, if any part of this telescope be covered, the remaining part will, nevertheless, gather and focus light just as though the whole lens were in action, only there will be less light collected at the focus within the tube. The small lens at the telescope's eye end is simply a magnifier to help our eye examine the image of any distant object formed at the focus by the large lens at the farther end of the instrument. For of this simple character is the operation of any telescope. The large glass lens at one end collects a distant planet's light and brings it to a focus near the other end of the tube, where it forms a tiny picture of the planet, which in turn is examined with a little magnifier at the eye end. Having arrived at this fundamental principle, that part of a lens will act in a manner similar to a whole one. It is easy to explain the construction of a heliometer. An ordinary telescope lens is sawed in half by means of a thin, round metal disc, revolved rapidly by machinery, and fed continually with emery and water at its edge. The cutting effect of emery is sufficient to make such a disc enter glass much as an ordinary saw penetrates wood. The two semi-lenses, as they are called, are then mounted separately in metal holders. These are attached to one end of the heliometer, called the head, in such a way that the two semi-lenses can slide side by side upon metal guides. This head is then fastened to one end of a telescope tube mounted in the usual way. The head end of the instrument is turned toward the sky in observing, and at the eye end is placed the usual little magnifier we have already described. The observer at the eye end has control of certain rods by means of which he can push the semi-lenses on their slides in the head at the other end of the tube. Now, if he moves the semi-lenses so as to bring them side by side exactly, the whole arrangement will act like an ordinary telescope, for the semi-lenses will then fit together just as if the original glass had never been cut. But if the half-lenses are separated a little on their sides, each will act by itself. Being slightly separated, each will cover a different part of the sky. The whole affair acts as if the observer at the eye end were looking through two telescopes at once, for each semi-lens acts independently, just as if it were a complete glass of only half the size. Now suppose there were a couple of stars in the sky, one in the part covered by the first semi-lens, and one in the part covered by the second. The observer would, of course, see both stars at once upon looking into the little magnifier at the eye end of the heliometer. We must remember that these stars will appear in the field of view simply as two tiny points of light. The astronomer, as we have said, is provided with a simple system of long rods, by means of which he can manipulate the semi-lenses while the observation is being made. If he slides them very slowly one way or the other, the two star points in the field of view will be seen to approach each other. In this way they can at last be brought so near together that they will form but a single dot of light. Observation with the heliometer consists in thus bringing two star images together until at last they are superimposed one upon the other, and we see one image only. Means are provided by which it is then possible to measure the amount of separation of the two half-lenses. Evidently, the farther asunder on the sky are the two stars under observation, the greater will be the separation of the semi-lenses necessary to make a single image of their light. Thus, measurement of the lenses' separation becomes a means of determining the separation of the stars themselves upon the sky. The two slides in the heliometer head are supplied with a pair of very delicate measures or scales, usually made of silver, and these can be examined from the eye end of the instrument by looking through a long microscope provided for this special purpose. Thus an extremely precise value is obtained both of the separation of the sliders and of the distance on the sky between the stars under examination. Measures made in this way with the heliometer are counted the most precise of astronomical observations. Having thus described briefly the kind of observations obtained with the heliometer, we shall now touch upon their further utilization. We shall take as an example but one of their many uses, that one which astronomers consider the most important, the measurement of stellar distances. Even the nearest fixed star is almost inconceivably remote from us, and astronomers are imprisoned on this little earth. We cannot bridge the profound distance separating us from the stars, so as to use direct measurement with tape line or surveyor's chain. We are forced to have recourse to some indirect method. Suppose a certain star is suspected, on account of its brightness, or for some other reason, of being near us in space, and so giving a favorable opportunity for a determination of distance. A couple of very faint stars are selected close by. These, on account of their faintness, the astronomer may regard as quite immeasurably far away. He then determines with his heliometer the exact position on the sky of the very bright star with respect to the pair of faint ones. Half a year is then allowed to pass. During that time the earth has been swinging along in its annual path or orbit around the sun. Half a year will have sufficed to carry the observer on the earth to the other side of that path, and he is then 185 million miles away from his position at the first observation. Another determination is made of the bright star's position as referred to the two faint ones. Now, if all these stars were equally distant, their relative positions at the second observation would be just the same as at the former one. But if, as is very probable, the bright star is very much nearer us than are the two faint ones, we shall obtain a different position from our second observation, for the change of 185 million miles in the observer's location will of course affect the direction in which we see the near star, while it will leave the distant ones practically unchanged. Without entering into technical details, we may say that from a large number of observations of this kind we can obtain the distance of the bright star by a process of calculation. The only essential is to have an instrument that can make the actual observations of position accurately enough, and in this respect the heliometer is still unexcelled. End of chapter 13.
Chapter 14 of Practical Talks by an Astronomer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Diana Schmidt. Practical Talks by an Astronomer by Harold Jacoby. Occultations. Scarcely anyone can have watched the sky without noticing how different is the behavior of our moon from that of any other object we can see. Of course, it has this in common with the sun and stars and planets, that it rises in the eastern horizon, slowly climbs the dome of the sky, and again goes down and sets in the west. This motion of the heavenly bodies is known to be an apparent one merely, and caused by the turning of our own earth upon its axis. A man standing upon the earth's surface can look up and see above him one half the great celestial vault, gemmed with twinkling stars, and bearing perhaps within its ample curve one or two serenely shining planets and the lustrous moon. But at any given moment the observer can see nothing of the other half of the heavenly sphere. It is beneath his feet and concealed by the solid bulk of the earth. The earth, however, is turning on an axis, carrying the observer with it, and so it is continually presenting him to a new part of the sky. At any moment he sees but a single half sphere, yet the very next instant it is no longer the same. A small portion has passed out of sight on one side by going down behind the turning earth, while a corresponding new section has come into view on the opposite side. It is this coming into view that we call the rising of a star, and the corresponding disappearance on the other side is called setting. Thus, rising and setting are, of course, due entirely to a turning of the earth, and not at all to the actual motions of the stars, and for this reason all objects in the sky, without exception, must rise and set again. But the moon really has a motion of its own, in addition to this apparent one caused by the earth's rotation. Somewhere in the dawn of time early watchers of the stars thought out those fancy constellations that survive even down to our own day. They placed the mighty lion, king of beasts, upon the face of night, and the great hunter too, armed with club and dagger, to pursue him. Among these constellations the moon threads her destined way, night after night, so rapidly that the unaided eye can see that she is moving. It needs but little power of fancy's magic to recall from the dim past a picture of some aged astronomer graving upon his tablets the records of the moon. To-night she is near the bright star in the eye of the bull, and again, to-night she rides full and near to the heart of the Virgin. And why does the moon ride thus through the stars of night? Modern science has succeeded in disentangling the intricacies of her motion. Until today, only one or two of the very minutest details of that motion remain unexplained. But it has been a hard problem. Someone has well said that lunar theory should be likened to a lofty cliff, upon whose side the intellectual giants among men can mark off their mental stature, but whose height no one of them may ever hope to scale. But for our present purpose it is unnecessary to pursue the subject of lunar motion into its abstruser details. To understand why the moon moves rapidly among the stars, it is sufficient to remember that she is whirling quickly round the earth, so as to complete her circuit in a little less than a month. We see her at all times projected upon the distant background of the sky, on which are set the stellar points of light, as though intended for beacons to mark the course pursued by moon and planets. The stars themselves have no such motions as the moon. Situated at a distance almost inconceivably great, they may, indeed, be travelers through empty space, yet their journeys shrink into insignificance as seen from distant earth. It requires the most delicate instruments of the astronomer to so magnify the tiny displacements of the stars on the celestial vault that they may be measured by human eyes. Let us again recur to our supposed observer watching the moon night after night, so as to record the stars closely approached by her. Why should he not some time or other be surprised by an approach so close as to amount apparently to actual contact? The moon covers quite a large surface on the sky, and when we remember the nearly countless numbers of the stars, it would indeed be strange if there were not some behind the moon as well as all around her. A moment's consideration shows that this must often be the case, and in fact, if the moon's advancing edge be scrutinized carefully through a telescope, small stars can be seen frequently to disappear behind it. This is a most interesting observation. At first we see the moon and star near each other in the telescope's field of view, but the distance between them lessens perceptibly, even quickly, until at last, with a startling suddenness, the star goes out of sight behind the moon. After a time, ranging from a few moments to perhaps more than an hour, the moon will pass, and we can see the star suddenly reappear from behind the other edge. These interesting observations, while not at all uncommon, can be made only very rarely by naked eye astronomers. The reason is simple. The moon's light is so brilliant that it fairly overcomes the stars whenever they are at all near, except in the case of very bright ones. Small stars that can be followed quite easily up to the moon's edge in a good telescope disappear from a naked eye view while the moon is still a long distance away. But the number of very bright stars is comparatively small, so that it is quite unusual to find anyone not a professional astronomer who has actually seen one of these so-called occultations. Moreover, most people are not informed in advance of the occurrence of an opportunity to make such observations, although they can be predicted quite easily by the aid of astronomical calculations. Sometimes we have occultations of planets, and these are the most interesting of all. When the moon passes between us and one of the larger planets, it is worth while to observe the phenomenon, even without a telescope. Up to this point we have considered occultations chiefly as being of interest to the naked eye astronomer, yet occultations have a real scientific value. It is by their means that we can, perhaps, best measure the moon's size. By noting with a telescope the time of disappearance and reappearance of known stars, astronomers can bring the direct measurement of the moon's diameter within the range of their numerical calculations. Sometimes the moon passes over a condensed cluster of stars like the Pleiades. The results obtainable on these occasions are valuable in a very high degree, and contribute largely to making precise our knowledge of the lunar diameter. There is another thing of scientific interest about occultations, though it has lost some of its importance in recent years. When such an event has been observed, the agreement of the predicted time with that actually recorded by the astronomer offers a most searching test of the correctness of our theory of lunar motion. We have already called attention to the great inherent difficulty of this theory. It is easy to see that by noting the exact instant of disappearance of a star at a place on the earth, the latitude and longitude of which are known, we can both check our calculations and gather material for improving our theory. The same principle can be used also in the converse direction. Within the limits of precision imposed by the state of our knowledge of lunar theory, we can utilize occultations to help determine the position on the earth of places whose longitude is unknown. It is a very interesting bit of history that the first determination of longitude of Washington was made by means of occultations, and that this early determination led to the founding of the United States Naval Observatory. On March 28, 1810, Mr. Pitkin of Connecticut reported to the House of Representatives on laying a foundation for the establishment of a first meridian for the United States, by which a further dependence on Great Britain or any other foreign nation for such meridian may be entirely removed. This report was the result of a memorial presented by one of William Lambert, who had deduced the longitude of the capital from an occultation observed October 20, 1804. Various proceedings were had in Congress and in committee, until at last, in 1821, Lambert was appointed to make astronomical observations by lunar occultations of fixed stars, solar eclipses, or any approved method adapted to ascertain the longitude of the capital from Greenwich. Lambert's reports were made in 1822 and 1823, but 10 years passed before the establishment of a formal naval observatory under Goldsborough, Wilkes, and Gillis. But to Lambert belongs the honor of having marked out the first fundamental official meridian of longitude in the United States. End of Occultations.